Due to the importance of ionization energy and its significance in determining many chemical properties of elements in the periodic table, we use two experimental methods to detect ionization energy. The very important part, the first is X-ray photoelectron spectroscopy. So we need the energy required to eject electron from an atom. So for that we have to strike the sample or the atom by another beam or another energetically possible rays. So we are using X-ray, in this case X-ray photoelectron spectroscopy. It is also known by the name Electron Spectroscopy for Chemical Analysis, ESCA. So, and the second is UV photoelectron spectroscopy. So, what is the difference between both two? So, ionization energy is simply the amount of energy required to take the valence electrons away from the atom. So, we have to take the electron from the atom. In another way, we can say that we have to remove the electron from the nuclear field of attraction, or the binding energy, the energy required to bind the electron to the nucleus is the binding energy of electron. So we are trying to take the electron by supplying some energy, by removing it by supplying some energy which is equal to ionization energy or the binding energy of electron. So we can also say that electron binding energy is equal to ionization energy. That is, electron binding energy is the amount of energy required to bind an electron to the atom or to the field of nucleus field of attraction. So electron binding energy is also termed as ionization energy. Okay. So the energy required to remove the electron from an atom or the field of attraction or from the field of attraction of nucleus can be done by either through its powerful source. So we are using X-ray for that. So let us take the illustration first. When in the case of X-ray, the energy, the wavelength or the frequency, the X-ray is having very high energy of the order of 200 to 2000 electron volt. So this X-ray will strike the atom's core electrons. Okay. The X-ray will strike the atom's core electron. As a result of that, this electron will get ejected. Okay. The energy required, the rejected energy, the ejected electron is move with a speed, and we are going to measure that speed with the support of kinetic energy in terms of kinetic energy. So we are measuring the kinetic energy of ejected electron, thereby understanding the ionization energy or binding energy. So what is the effect of ultraviolet photoelectron spectroscopy? When ultraviolet rays is having very small frequency or very low energy, so it is of the order of 3 to between electron volt. Okay, so as a result of that, it will attack only the valence electron, and this is core electron. This is the nucleus. So X-ray will strike the core electron, whereas UV light will strike the valence electron. So we require ionization energy corresponds to this valence electron. So most commonly we are using ultraviolet photoelectron spectroscopy for understanding the ionization energy. But the issue is that ultraviolet rays are very weak as a result of that the recorded spectra, we are getting a record spectra after this process. The spectra is very low in resolution, hence we are following XPS or depends on XPS, X-ray photoelectron spectroscopy, to determine the ionization energy or electron binding energy. X-ray photoelectron spectroscopy, or ESCA, the electron spectroscopy of chemical analysis. We are going to explain the concept briefly. It is a surface characterization technique. For surface characterization of an element or a solid state, whether it is solid, liquid, or film or bio state, we require microscopic technique, also spectroscopic technique is there. So here we are using electron spectroscopy. A electron spectroscopy means when a beam of light or a source of incident rays are incident or strike the surface of sample, and high energy electrons are ejected from the surface. So we are going to analyze the ejected electrons and to determine their velocity in terms of kinetic energy and plot it. Okay, and that plot is called spectra. So here XPS, X-ray photoelectron spectroscopy, where X-ray is the striking the source to strike the surface of the sample. So which is used for the surface characterization to determine chemical composition of a sample, structure of that sample, whether what kind of structure is occur, oxidation state of that particular molecule or the atom, and dynamics. Dynamics means how they are oriented and what is the dynamics of electron in it. Everything, almost all details we can get it from XPS result. The XPS can be used for all the elements except hydrogen and helium. Okay, because the reason you may have a doubt that why we XPS is not used for hydrogen and helium, because hydrogen and helium is having no core electrons, only they have oneness electrons which is very highly bound to the nucleus and there is no core electrons. That's the reason. So this XPS or ESCA was invented by a Swedish physicist Kai Zygmunt in 1954. For that invention, he got Nobel Prize in Physics in 1981. The what exactly we are getting from XPS? We are getting a spectra like this, where we are plotting the power of electron or the number of electron in the y-axis, number of electrons or power of electron as a function of energy or frequency or lambda. The energy, what kind of energy? It can be binding energy or it can be kinetic energy of the electron we are collected from, we have analyzed from the result. So the plot, the XPS plot spectra contain in the x-axis, in the horizontal axis, energy, binding energy or kinetic energy, or can be represented in terms of frequency or lambda, and and in the y-axis it will be power of electron generated or the number of electrons generated. So the plot is always power or number of electrons as a function of energy, frequency, lambda. What is the principle? The theory part. Theory part. When an X-ray which strikes the, when an X-ray, this is the sample space. When an X-ray having h nu is the energy, right? When strike the sample, the electrons on the sample get ejected. Right? This is the sample space. So this sample X-ray strike with an energy h nu. H is the Planck's constant and nu is the frequency of X-ray light. Electrons get ejected like this. Okay, this ejected electrons is having a kinetic energy. Okay, that kinetic energy, and VE is the velocity. VE is the velocity of electron. M is the mass of the electron. So kinetic energy, that ejected electron, which is we collected, which kinetic, that electron, the speed of that electron or the kinetic energy we have recorded with the support of an analyzer. So what is the kinetic energy of this electron is equal to the source energy minus binding energy. Binding energy is the amount of energy required to remove that electron from the atom. Or it can be also say that the amount of energy required to remove an electron from the field of attraction of nucleus. So that is called That's called ionization energy or electron binding energy. So through XPS, we can find out the electron binding energy, from which we can also find out ionization energy, the amount of energy required to remove an electron from the field of attraction of nucleus. So binding energy plus phi. This is called work function. Work function is the minimum amount of energy required to remove an electron from a surface, a metal surface. The minimum amount of energy required to remove an electron from the metal surface, which is a constant, which is depends on the type of the metal, which is a constant and depends on the metal surface, which is already been calculated and it is available. Experimentally, it is calculated for every metals, and we can apply which type of metal is using. We can apply that in through system. So the the kinetic energy of the ejected electron can be calculated by half mv square is equal to the energy of the X-ray, the source beam, minus binding energy of the electron minus work function. Okay, this is the principle of X-ray photoelectron spectroscopy. Now we will discuss the illustration of the experimental technique of XPS. So in XPS, there are mainly five parts are there. One is the source X-ray beam source. Second is the sample and sample holder. Third is the analyzer, a hemispherical analyzer, which is an electron energy analyzer. Okay, in order to get a high resolution result. And fourth is an electron detector. It can be a multiplier or a transducer to generate more pulses to get a most prominent result. Third is a fifth is a signal processor or a recorder, which can amplify the received pulses. And finally, we are getting the spectra. So one by one, we will discuss. This is the illustration. This is the source cathode tube, a cathode tube, which is a monochromatic crystal, uh, which is having an X-ray source by incidenting the ray to magnesium or aluminum metal. So the monochromatic crystal, a cathode with an X-ray source getting from magnesium or aluminum metal, and the bandwidth of X-ray, it should be zero point 0.3 electron volt, and the potential of X-ray beam is 200 to 2000 electron volt. That is potential or the energy. The energy of the X-ray source is 200 to 2000 electron volt. That is the energy range of the spectra in the x-axis, 200 to 2000 electron volt. Or sometimes it is seen that it is 200 to 1500 or below 200 also. We can control the power, the energy of X-ray, thereby getting whether it can hit the core electron or the valence electron or not. So we can control, we can adjust the energy of X-ray, because as you all know that X-ray beams are hitting the core electron. This is the nucleus. X-ray beam is hitting the core electron. So we need ionization energy there from where the valence electron. So we can control the energy of X-ray by hitting the valence electron instead of avoiding ultraviolet spectroscopy. So this is the energy of X-ray. So this cathode tube. This is the cathode tube. By generating the X-ray from magnesium or aluminum metal, the cathode ray tube, the X-ray beam hit the sample part. The sample source. This is the sample holder where we are keeping the sample. The sample holder must be in high vacuum in order to avoid any contamination. If any contamination is there, the result will be wrong. So it should be at a pressure of 10 raised to minus 5 torr. Torr is the pressure unit. the sample holder must be in the entire equipment. The entire equipment must be in a vacuum in order to avoid contamination or dust. So when the X-ray hit the sample surface, the electrons are rejected. The electrons are rejected, and which is collected, which is passed through a lens, which is focused. The rays are focused and moved through a slit, a hemispherical analyzer with a slit entrance. Okay, inside the slit, the hemispherical analyzer, there, the electrons attain a curvature, a curved path. This curvature, the hemispherical analyzer, is known as electron energy spectrometer, which is in a high electrostatic field, which is placed in a analyzer is a very high electrostatic field. So the result will be depends on the resultant kinetic will be the curvature of electron. The curvature, the path of the electron is depends on the electrostatic field as well as the kinetic energy of the electron. So we can say that this path, this curvature, the radius of the curvature depends on kinetic energy of electron and electrostatic field. Electrostatic field. Electrostatic field. Okay. The both it depends upon the kinetic energy of electron and the electrostatic field. Okay, force of attraction. So the ejected electron attains a curved path, and this equipment, the analyzer is placed in a pressure of 10 raised to minus 5 torque. So, and in order to get a very high resolution result, we are using electron energy spectrometer, which is a hemispherical analyzer. And the curvature, the electrons, the ejected electron beam, which attains the curved path, which pass through the slit exit and move to, this is a single beam, move to a multiplier. This is called electron detector. We are collecting that beam from the analyzer. If a single, see, this is the illustration of the multiplier. When a single beam of, this is an electron beam, a single beam of electron is passed through the multiplier. The multiplier sides are, okay, the multiplier sides are coated with the lead or vanadium metal. Okay, this lead or vanadium metal will split the single beam into multiple pulses. As a result of that, the result will be more prominent. We will get a proper result. Otherwise, the result will be in vague. So, the surface of the multiplier is coated with the lead and vanadium. So, a single beam of electron will get doubled or tripled, or number of times of pulses are generated. That will be supported by this electron detector. Finally, those pulses are processed by the detector, and we obtain the actual spectra, the XPS spectra. So let me repeat it simply. The first part is the X-ray source. Second is the sample holder. Third is the hemispherical analyzer. And the electron beams are collected at the fourth electron detector. And finally, a signal processor or detector, we get the spectra. First, the X-ray beams are generated from the cathode tube, which hit the sample, and the injected electrons are passed through a hemispherical analyzer. The curvature, the path of electron depends upon the electrostatic field and the kinetic energy of the electron. The beam of electron is collected by a multiplier or transducer or electron detector, which is then finally processed at a signal processor or detector with the support of a computer, and we will obtain the spectrum. This is the illustration, the technical illustration or experimental illustration of a schematic diagram of that's the correct name, schematic diagram of an XPS spectroscopy. So you should write, you should draw this for your reference. So we have learned the schematic diagram of XPS spectroscopy. Move on to the concluding part. We know that X-ray beams are very high in energy, so it hit the core electrons. As a result of that, we can learn, we can study the surface. We can study the surface of sample, surface analysis of sample. This is the sample. If X-ray hit, they can study up to a depth of 5 to 10 nanometer below the surface. Okay, 5 to 10 nanometer below the surface. That's the reason why it hit the core electron. X-rays are hit the core electron, so it will move into the sample. So we can study the chemical compositions and dynamics and all the features of the given sample at a depth of 5 to 10 nanometer inside from the surface. And if we can control the energy of the X-ray beams, we can also able to study the valence electrons, and thereby, if the valence electrons are rejected, thereby we can calculate the ionization energy. Why we use XPS rather than UPS? UPS means ultraviolet photoelectron spectroscopy, because ultraviolet photoelectron spectroscopy, due to the use of very weak ultraviolet beam, the resultant spectra, the resolution of the resultant spectra is very poor. So we can, if if the core electron, if this is the valence electron and this is the core electron, X-ray can only be used for core electron. If we can control the energy of X-ray beam, we can use it for studying the valence electron. Okay, and in ultraviolet spectroscopy, the discharged tube with helium generate the UV light. That is the only difference between X-ray, XPS and the UPS, because we are using an UV source instead of an X-ray source. A UV source is a discharged tube with a helium gas, which is of the order of 10 to 45 electron volt is the energy, which is very poor. So that's the reason. And the third is in the spectra. In the spectra of XPS, we have already learned that number of electron is plotted, or power of electron is plotted against the function of energy. It can be kinetic energy of binding energy. The binding energy of the order 1252 electron volt to 0. So it is plotted from 1250 here, 0 here. Likewise, binding energy is plotted, whereas kinetic energy is plotted at the initial value is 250 to 1500 electron volt. Kinetic energy, it is kinetic energy. So, and if a spectra will get what it shows, the peak shows the height of the peak shows the number of electrons. In the height of the peak shows the number of electrons ejected, and the position of the peak shows the environment, the composite, the environment of the atom. The environment belongs to that particular electron belongs to which environment in an atom, and the bond type or the subshell type. Let us consider an example. If we take the XPS of boron is having 5 atomic number, 1s2, 2s2, 2p1. The XPS spectra of boron will be, this is boron, XPS of boron. 1s will comes because the amount of energy required to, this is ionization energy, this is or bonding energy. Bonding energy is represented like this, 1250 to 0. So the amount of energy required to remove the 1s electron is very, very high, because it is very close to the nucleus. So nuclear charge is very high. Ionization energy required is also more. So this is belongs to 1s. The number of electrons represent 2. And the 2s and 2p is having very less energy when compared with the core electron 1s. So 2s and adjacent peak shows 2p. Because of very weak screening effect, 2p experiences very less electron nuclear charge. So the peak will comes after 2s. So this is the 3 peaks represent 3 subshells of boron. This is an example. Okay. So I'm just briefing the concept only here, not an advanced level. So this is only for the theoretical and the part in MSc Classes for plus one, plus two, and degree. There is no class, no discussion on. There's in the syllabus nothing about XPS or ESCA. Only in MSc there's an installation bar studies about XPS and ESCA. So you should give an example of this one, this boron case. If in question, if they ask an essay on XPS instrumentation, you can give an example of boron here. So the three peaks represent the three subshells of boron. Okay. So and what is the advantage of XPS? It is a surface technique. The most important advantage is that the sample is not destructible because sample can be used for further analytical methods also. If we can use a sample for XPS, we can use the sample for any other analytical methods. It is not a destructible one, and it is very surface sensitive. It not only gives the composition but also gives the structural analysis, oxidation state of the atom, and many things, whether the sample is contaminated or not. And also the X-ray beam, due to the high energy of X-ray beam, it is move inside the sample to a depth of 5 to 10 nanometer inside through the surface. So it will give the inner electronic configuration, inner electronic structure and dynamics, and the positions of atoms, structure, arrangement also we will get from XPS. The only drawback is that it give we can use all the elements in the periodic table to study using XPS except hydrogen and helium due to the absence of core electron. Okay, so XPS or XPS or ESCA, electron spectroscopy for chemical analysis, is one of the very important spectral analysis used widely in research area. Okay, thank you.